So, we are looking at the problem of the manufacturer trying to produce, trying to change his strategy of producing more chairs. So, in the first week he is able to produce 1200 chairs and he has the option of increasing his production by 80 chairs. So, we wanted to generate the data and we said that if this is the first week production, then the data generated second week would be 1200 plus 80, third week will be A2, the second week plus 80 more and so on. So, 10th week it will be 1200 plus 9 times 80, that will be so much. So, this gives us a ordered collection. So, important thing is this data is an ordered collection of numbers. So, this is the first week, second week, third week, 10th week, and it has a special property, namely the difference between any two of them, the of say A10 and A9 is 80 and the previous one is A3 minus A2 is 80 and so on. So, this is the data generated and this is the order collection of numbers. You see, if A10 was equal to this, what will be A11? So, it will be 1200 plus 10 times 80 and so on. So, that one motivates one to guess that if I am looking at the nth week, n could be anything 10, 15, 20 and so on. So, the nth week production will be A1 plus n minus 1 times d. What is d? That is the increase per week that we are making. Okay. In our case, it is 80. So, that means if we want to look at the output to exceed 8000 chairs, then this number A n should be bigger than 8000. So, that means A n is equal to 1200 plus n minus 1 into 80, that should be bigger than 8000, and that means if we simplify this equation, that is n minus 1 times 80 is bigger than 6800. So, this implies, that means n minus 1 should be 6800 divided by 80, that is 85. So, that means n should be bigger than or equal to 86. So, after 86 week, the number of chairs produced will be 8000. So, this is how a ordered data is generated and a problem is solved. We can try to solve the problem similarly for the option B. So, in the option B, A1, the first week production was 1200 and there is an increase of 5% per week. That means, whatever amount is produced in a week, next week it is increased by 5%. So, what will be A2? A2 will be 1200 plus 5% of 1200. So, that will be this. So, this will be the amount that will be produced next week. And what will be A3? It will be A2 plus 500, 5% of 1200. So, that will be this. So, that means it is there is a typo here, it should be 1200 multiplied by 1 plus 5 over 100. So, if you continue at the 10th week, this will be the amount of production that will be produced. Okay. So, again, by the given formula, that is a 5% increase, okay, we are able to find out what is the 10th week. So, this gives us that a formula probably that at nth, after n weeks, the production will be this much. So, if you want the production to increase, right, you want to find out when will if there is a 5% increase every week, when will the production go beyond 8000, then we have to say that A n, which is equal to this, is bigger than 8000. So, this equation now one has to solve, and to solve that one uses log tables. So, that can be solved. But the important thing is, in this problem, you are first able to generate an ordered data, a data of numbers A1, A2, A3, where there is an order, this is the first one, second one and so on, and then able to analyze the data. So, this motivates the following definition of a sequence. A sequence of elements of a set is an ordered collection of that set. So, ordered means there is order, you pick up an element, call it the first, call it the next, pick up another one, call it the second one, and so on. The first element is A1, let us say A1, the second element you can call it as A2, and the general nth element as An. So, this gives us a ordered collection A1, A2, A3, and so on, which is normally written as a curly bracket An, the nth term, n bigger than or equal to 1. So, a sequence is an ordered collection of numbers and is denoted by this symbol An. So, we say a sequence is a arithmetic sequence if the difference between any two consecutive terms is a constant. That means, An plus 1 minus An is the same constant d, then we say this sequence is an arithmetic sequence, and that is what happened in our previous case of the option A, when there was increase of 80 chairs per week. Okay. So, this is, and this d is called the common difference. So, the sequence looks like the first term is A1, the second is A2, which is A1 plus d, the third time is A2 plus d, that will be A1 plus 3d, and so on. We say the sequence, the nth term of the sequence will be A1 plus n minus 1d, right, in the arithmetic sequence. We say a sequence is a geometric sequence if the ratio of the two consecutive terms is same. Okay. So, An divided by An minus 1 should be equal to R or n bigger than or equal to 1. There is no A0. So, better way of writing that will be n bigger than or equal to 2 is a constant. So, this is called a geometric sequence. Okay. So, n is equal to, for example, if you take the sequence of numbers, okay, n is equal to n, that is a arithmetic sequence. Okay. And similarly, if I take the sequence say Gn equal to 2n plus 1, okay, odd numbers, that is also a arithmetic sequence. So, that example of first week, second week, two choices, right, that gave us the notion of arithmetic and geometric sequences. Okay. Let us look at another example which normally students of economics, commerce encounter. This is interest. Suppose an amount P0 is invested at a rate of R% per year with a simple interest. Means every year the investor will give, instead of, this is a typo here, instead of set it should be get. The investor will get P multiplied by R over 100 amount. So, if P1, P2, P3 denotes the principal amount along with the interest being earned, then P1 will be P0, the starting point, plus P0 divided by R by 100. So, this will be the amount. What will be P2? Okay. So, P2 will be P0 plus, right, that is P1. So, P2 and so on. So, this gives us a arithmetic sequence with common difference as P0 divided by, okay, R plus 1. If the amount is calculated as a compound interest, then the scenario changes. So, R% per annum, that means the interest also get interest on that. So, P1 will be equal to P0 plus P0 by R, that is P0 multiplied by 1 plus R by 100. P2 will be P1 plus whatever you have earned after 1 year, you will get interest on the whole amount. So, it is P1 multiplied by R over 100. So, that will be, if we put the value of P1, that is P0 into R by 100. So, this is P0 multiplied by this and so on. So, at Pn, after n years at the rate of R% interest, this will be the principal would have grown to this much. So, again this generates a sequence, an ordered collection of numbers, which in fact is a geometric sequence with common ratio as 1 plus R over 100. So, the principal, if there is simple interest, that gives us a sequence of numbers, the amount Pn is a arithmetic progression. If it is a compound interest, it is a geometric progression. And in each case, one would like to know what happens to the terms of the sequence A n as n changes, n becomes large and large. Of course, if it is a interest, right, the principal will keep on growing. Okay. And similarly, in the example of production of chairs, also it will keep on increasing. Okay. But in a general sequence, that need not happen always. So, let us look at some example. For example, consider the sequence A n equal to 1 over n. So, let us write the sequence. So, A n is equal to 1 over n. So, what is A 1? So, that is equal to 1. What is A 2? That is 1 by 2. What is A 3? That is 1 by 3, and so on. So, it is quite clear that A 1 is bigger than A 2, A 2 is bigger than A 3 is bigger than so on. So, it is quite clear that this sequence 1 over n is a decreasing sequence. The values are decreasing. First value is 1, second is 1 by 2, third is 1 by 3. So, values are decreasing and it is coming closer and closer to the value 0. Let us look at the sequence A n equal to minus 1 over n. So, what will be the terms of the sequence? When A n is equal to minus 1 by n. So, what is A 1? A 1 will be equal to minus 1. What is A 2? A 2 is minus 1 by 2. What is A 3? Equal to minus 1 by 3, and so on. So, if I try to plot it, it is 0, here is minus 1, here is minus 1 by 2, here is minus 1 by 3, and so on. So, it is quite clear that the sequence is an increasing sequence. As you move, the terms are increasing, the values are increasing and coming closer to 0. Let us look at the sequence A n minus 1 to the power n divided by n. What are the values of this sequence? So, let us write that again. So, A n is equal to minus 1 to the power n divided by n. So, what is A 1? N equal to 1. So, this is minus 1. What is A 2? Minus 1 square. So, that is 1 by 2. What is A 3? So, minus 1 to the power 3, that is minus 1 by 3. A 4 will be equal to 1 by 4, and so on. So, let us look at, so this is the point 0, right, and this is A 1 is minus 1. What is A 2? A 2 is 1 by 2. What is A 3? Is minus 1 by 3. What is A 4? Is 1 by 4. So, again we observe that this sequence is neither increasing nor decreasing, it is fluctuating. Some alternatively it is becoming positive and negative, and but still it is coming closer to 0. Let us look at one more example of a sequence A n, where A n is equal to minus 1 to the power n. So, what is happening to this sequence? So, A n is equal to minus 1 to the power n. So, if I try to plot it, it is 0 here. So, n equal to 1, I will get A 1, which is equal to minus 1. What is A 2? A 2 minus 1 to the power 2, that is 1, that is A 2. A 3 will be equal to again minus 1, A 4 will be equal to again 1, A 5 again here, A 6 here. So, all the odd terms will be at minus 1, all the even terms will be equal to 1. So, it fluctuates minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. So, this sequence is neither increasing nor decreasing, it fluctuates at the values minus 1 and plus 1, it does not come closer to any value. So, a behavior of a sequence depends on what is the sequence. So, let us consider a sequence called 1 over n bigger than or equal to 0. As we observed, this sequence becomes, terms of the sequence become smaller and smaller. First term is 1, second is equal to 1 over 2, third is 1 over 3, and smaller and smaller. It is coming closer and closer to 0. In fact, it is approaching, we can say it is approaching 0. It comes close to 0, as close as we want it. The distance of a n from 0, I can make it as small as I want. So, this distance is actually equal to 1 over n, and I can make it less than epsilon by choosing n large enough. Let us formalize this as a definition. A sequence a n is said to converge to a value L which is a number. If there exists a number L, we say a sequence converges if there exists a number L. So, here is a number L which has the property that given any number epsilon, this is a Greek letter epsilon, given any number epsilon bigger than 0, okay, if I look at L minus epsilon and L plus epsilon, then what should happen? All the terms of the sequence a n should lie between L minus epsilon and L plus epsilon for all n bigger than or equal to 0. So, I can write this also as the distance between a and L is less than epsilon for all n bigger than 0. Let us try to understand this. This is quite a subtle point. See, we want to say that the sequence is approaching this value L. So, intuitively what it means that a n should come closer and closer to L. So, how close? So, I will specify beforehand that the margin of error can be at the most this distance. So, this is specified by a number epsilon bigger than 0. So, it says that I should be able to find a interval around L of length 2 epsilon. So, if I look at L minus epsilon and L plus epsilon, then all the terms of the sequence are inside this interval for n bigger than or equal to 0. So, that another way of saying that would be that given epsilon bigger than 0, given that is an error I can make, you can think of a n minus epsilon is a n is the value of the sequence, L is the expected value of the sequence. This is the error I am making, a n minus epsilon mod is the error I am making. Okay. This is the distance, that is how far away it is from L, that is the error. That error should be less than epsilon for which n? For all n. That is the important thing, that from some stage onwards everything should fall in between. Okay. That means possibly a 1, a 2 up to a n naught minus 1, these terms are outside somewhere, but after that n naught stage, the tail of the sequence, you can think it as a tail, that a 1, a 2, a n naught minus 1, a n naught onwards, that is the tail of the sequence, that should lie in between this interval. Then we will say that the sequence a n converges to L, that is the limit. So, we say that a n converges to L and write it as limit n going to infinity a n equal to L. So, this is only a symbol, this is only a symbolic way of writing this thing, that given epsilon bigger than 0, there exists a stage n naught, there exists a stage n naught such that for all elements of the sequence bigger than or equal to n naught, they are lie at a distance epsilon from a n. So, convergence of a sequence means a tail of the sequence comes closer to L by at the most a distance 2 epsilon, and that epsilon is I will prescribe. Stage you have to find if you want to show limit of a n is equal to L. Okay. So, this is the convergence of a sequence, limit a n is equal to L. So, once again let me say, we say that a sequence a n converges if there is a number L such that for every epsilon bigger than 0, there exists n naught, a natural number such that a n minus L is less than epsilon for n bigger than n naught. Okay. Right. Let us look at some examples to understand this. Note that the sequence we had 1, 2, 3, 4, so on, and the sequence -1 to the power n, both are not convergent. Okay, let me just say that when a sequence is not convergent, we say it is divergent. Okay, I have not said that. So, let us say when a sequence is not convergent, we will say it is a divergent sequence. So, the sequence n is not convergent. Why? Because first term is 1, second term is 2, third term is 3. So, it keeps on increasing. It is not coming closer to any value. So, it is divergent sequence. Minus 1 to the power n, this is again divergent, because again it is not coming closer to any value. It is fluctuating between minus 1 and plus 1. One can write a proof of this, that this is not divergent. This is a divergent sequence, not convergent, by just now we said epsilon. We can, so when it will be slightly quite interesting and logical to write a proof of the fact that minus 1 to the power n bigger than n is a divergent sequence, is not convergent. Try to write a proof yourself. If not, try to read that web course on calculus that I have said. A complete proof is given there, right. But intuitively, this is, it fluctuates between minus 1 and plus 1, and that this is not convergent. It is a property of real numbers. Intuitively, it keeps on increasing. Okay, it is not coming closer, and this is divergent. So, there are different reasons for this sequence being not convergent. Okay. Let us look at the sequence n over n plus 1, n bigger than or equal to 1. We want to understand whether this sequence converges or not. The one way of analyzing this would be, write a few terms of the sequence and see what is happening. What is the first term? 1 over 1 plus 2. So, let us just write a first few terms of this sequence, what is happening. So, n divided by n plus 1. So, that is a n. So, what is a 1? That is 1 by 2. What is a 2? That is 2 by 3. What is a 3? 3 by 4. A 5, 4 by 5. So, from here, can you guess what is happening to the sequence? So, first term is 1 by 2, second is bigger than 1 by 2, that is 2 by 3, third is bigger, okay, that is 3 by 4, this is bigger. So, it seems it is going further and further, increasing, but it is n over n plus 1, it cannot go beyond 1, this is always a fraction less than 1. So, it is increasing towards 1. So, guess is probably it is convergent to 1. Okay. So, let us analyze this. So, look at n over n plus 1, I can factorize it by this way. So, it is 1 minus 1 over n. Okay. So, this part intuitively becomes 0 as n becomes larger and larger. So, this is becoming smaller and smaller. So, this is becoming smaller. So, intuitively this should go to 1. So, one guesses that the limit should be equal to 1. But there we will have to say why this is happening, because this is not a sequence, it is 1 minus 1 over n, it is something else. This is subtracted from here. So, to justify this kind of a thing, let us look at the distance between. So, this is how we guess that limit should be equal to 1. To prove it, let us look at a n minus 1. So, we have guessed L is the limit. So, a n minus L, this is this quantity, it is equal to 1 over n plus 1, and I can make 1 over n plus 1 small by choosing n large enough, okay, by choosing n large enough. So, that means I can say that this can be made less than epsilon for any given epsilon. So, this is how rigorously you will prove that this limit is equal to 1. At this stage, one can ask a question, can a sequence have more than one limit? One can prove that if a sequence has a limit, it is unique. There cannot be, intuitively it is quite clear, the tail of a sequence cannot come closer to two different values, right. Geometrically it seems impossible, but one can prove it rigorously. We will not go precisely into that. Okay. And we also saw that the sequence n is not convergent because it keeps on increasing. So, this motivates our next definition, namely we say a sequence a n is bounded above if there is a number alpha such that all the terms are less than or equal to alpha. That means, the terms of the sequence cannot go on the right side of alpha, there is a barrier. So, then we say it is bounded above. And similarly, we will say a sequence is bounded below if there is a number beta, so that all the terms of the sequence are on the right side of it. So, a n is bigger than or equal to beta okay, for all n, then we say a n is bounded below. So, bounded below is there is a barrier on the left, bounded above is barrier on the right. So, bounded below, bounded above. If a sequence is both bounded above and below, we say it is a bounded sequence. So, bounded means there is a barrier below, there is a barrier above, then we say it is a bounded sequence. So, examples, this sequence is bounded because for all n, absolute value of this is 1 over n square less than 1. So, all the terms of the sequence will lie between minus 1 and 1. So, there is a bound below minus 1, there is a bound below above 1. But boundedness at present does not say anything about the convergence of a sequence, keep that in mind. So, this sequence 2 to the power n divided by n square is not bounded, that one can show with slight amount of work, namely 2 to the power n grows much faster than n square. So, one has to write something, one has to do some more work, this is not bounded. Okay. Let me those of you who are more enthusiastic should try to prove 2 to the power n is bigger than n square is bigger than n for all n bigger than or equal to 5. That means, 2 to the power n will take over n square and it will take over even n for n bigger than or equal to 5. So, it will keep on growing, it will never converge. So, we will stop here for today, that having recalled that we have defined the notion of a sequence. Sequence is an ordered collection of numbers which essentially come from a data which is taken at different time points you can think of, and then a sequence may behave differently depending on what is the sequence. It may come closer and closer to a value, it may keep on increasing, it may keep on decreasing and so on. So, we defined the notion of convergence of a sequence. We say a sequence a n converges if there is a number L such that the distance between a n and L becomes small, less than epsilon for any prescribed epsilon from some stage n naught onwards. That stage n naught may depend on epsilon, but what should happen is absolute value of a n minus epsilon should be less than epsilon for all terms of the sequence n bigger than or equal to 0. That means, the tail of the sequence should come in a neighborhood of L of length epsilon. So, convergence of a sequence depends on the tail of the sequence. So, we will continue our study of sequences in the next lecture. Thank you.